right. I think we can get started. I'll start to introduce Professor Kamil Ugurbil. Professor Kamil Ugurbil is a distinguished scientist widely recognized for his significant contributions to magnetic resonance imaging. He is an esteemed member of the U.S. National Academy of Medicine and the American Academy of Arts and Sciences, and has been honored with many prestigious awards, and has also been awarded 2 honorary doctors in recognition of his impact on healthcare technology. Professor Ugurbil is the founding director of the Center for Magnetic Resonance Research at the University of Minnesota. His groundbreaking work has focused on developing and applying MR methods and instrumentation to achieve high spatial temporal resolution and high accuracy in both functional and anatomical brain imaging. This includes the pioneer introduction of functional brain imaging, development of ultra-high magnetic fields bigger than 7 Tesla, and highly accelerated functional brain imaging techniques. Professor Ugurbil's role as one of the 2 PIs of the Human Connectome project, and his participation in the inaugural working group of Brain Initiative further underlines his leadership and innovative spirit in advancing neuroscience research. We're very honored to have you today. Please go ahead, Professor Ugurbil.
Thank you very much, for both for the invitation and also for that kind introduction. I am sorry that I am not there in person to give this talk. That's what I was planning. Unfortunately, COVID infections are on the rise, and I did contract COVID just before traveling to this meeting. So we decided to hold the lecture online. I would prefer to be there in person and meet all of you as well as the other speakers as well. Well, the title I gave was Beyond the Human Connectome Project, and I changed it a little bit. I called it, I turned it around. The Human Connectome Project and Beyond is the title, because I want to start by actually talking about the original Human Connectome Project and what we've accomplished, and then use that as a good starting point to talk about where we want to go in the future with respect to acquiring data which is like the Human Connectome Project data. So we know that NIH invests substantially, something like $8 billion a year in neuroscience and brain disorders research. But despite that, actually, there's a feeling that we have not over the years not accomplished very much in terms of tackling the challenges posed by these disorders. And as a result, there was an initiative at NIH at some point, starting around 2010, to launch these major multi-institutional projects, and one of which was the Human Connectome Project. And the other big initiative is, of course, the brain research through advancing innovative neurotechnologies. And both of these have been trendsetters, and throughout the world right now, in many different countries, there are very similar projects that are going on. And as I mentioned, that this is really a response to the fact that brain disorders are increasingly the dominant source of disability in the United States, and as shown by this data that I'm showing you, neuropsychiatric disorders are more prominent in terms of disability than cardiovascular disease, neoplasms, etc. And yet, as I had mentioned, that there has not been major advances in tackling this disease. And there are thought to be certain diseases, so the Connectome Project and many of the Brain Initiative projects are in fact aimed towards defining the circuits and understanding circuits. So in the original Human Connectome Project, we were charged with describing the functional and structural connections among brain matter locations in the human brain using as high a resolution as possible. But of course, in the human brain, that still means, even today, in the millimeter scale. So we used spontaneous fluctuations in fMRI time series, so-called resting state fMRI, to deduce functional connectivity, and diffusion-weighted MRI to infer structural connectivity. And the Human Connectome project from the very beginning was structured so that it would also gather morphological imaging, task fMRI, a lot of phenotyping and genotyping. And all of these were really accomplished in the HCP. Now, there were really two Human Connectome project grants, but the main one was the one where I was involved in as co-PI with Van Essen. And it's known as the WashU-UMin consortium, but in terms of scientific collaboration, it really involved three institutions, that's Washington University, St. Louis, University of Minnesota, and Oxford in the UK. So it had two phases. One was the develop and optimize the tools that we are going to use in this project, and the second phase was to generate a 1,200 subject database using twins and their non-twin siblings at 3 Tesla, as well as, which is a less known part of the Human Connectome project, 200 subject database obtained at 7 Tesla. So the organization was as shown here. We at the University of Minnesota were responsible for the development of the hardware, all the pulse sequences and image reconstruction algorithms. Oxford was responsible for data cleanup and analysis for resting state fMRI and diffusion imaging, and WashU was also involved in data analysis, visualization, and dissemination. And David Van Essen and Matt Glazer was really leading the effort in WashU. So this is one of our all-hands meeting of the Human Connectome project. This picture was taken at WashU. And there were, as you can see, 10 institutions involved, but primarily it was WashU, University of Minnesota, and Oxford. And I can point to at least, I cannot identify all these individuals for you, but I can at least point to David Van Essen, who was my co-principal investigators in that effort. So I won't go into all the details about what kind of approaches we've used, what kind of parameters that we came up with. There is this paper, the Human Connectome Project Imaging Approach, which details all of this. So if you're really interested in digging deep in this, you can go to this particular paper. And of course, it has a lot of other references in it to other reasons why we have done what we have done in the Human Connectome Project. But what I would like to point out is that this is a big data project, and I put big data in quotes because of the fact that it's not really a huge data of the kind that, for example, Google collects, etc. But nevertheless, it's a big data project. It had a critical technical development component, which is a very important point, I think, about the Human Connectome project, and I think it also accounts for its success, and I will give you some metrics that indeed it has been a very successful project. And it was tasked with generating a large, publicly available human brain imaging data set, and Human Connectome data is publicly available, and I wouldn't be surprised if most of you in the audience have accessed this data and used it for various projects. So it was also restrictive. It was not comprehensive in terms of the people that we were focusing on. It was focused on normative adult population, ages 21 and 30. Now the challenges we faced at the beginning of the HCP was, okay, we were tasked with attaining as high a spatial resolution over the whole brain as possible. And of course, we are using magnetic resonance imaging techniques because of the fact that this is really the only methodology available at the present then and even now for studying the human brain for these kinds of connectivity measures. And so we have to maximize signal-to-noise ratio, and then we have to also increase data acquisition speed without sacrificing SNR. And that's actually a very critical point. And many of you may have realized this since you are probably using Human Connectome project sequences, but let me just sort of dwell on that a little bit. So there's always a trade-off between spatial resolution and temporal sampling rate. For example, if you think about imaging, whether it is 3D or multi-slice. I mean, you have to collect in a volume, in imaging a volume, you have to collect multiple slices. So, if you have higher resolution, you have to have more slices to cover the whole brain. And that means that since you have to acquire more slices, it takes longer to acquire them because each slice takes a certain amount of time to cover. So as a result, for example, if we have a diagram, this two-dimensional diagram, where we plot resolution versus sampling rate, which is like 1 over the TR being the amount of time we take to cover the whole brain, you may be operating, somewhere, let's see if I can get my cursor, right there. Let me pick up my laser, if I can. So you may be operating right over here, for example, and what we did in the Human Connectome project, actually we were working on it before the Human Connectome project, but Human Connectome project was the first platform where we deployed this in such a great extent. And what we did is we pushed this scale to over here, where we can actually, for a given resolution, we can increase the sampling rate, in fact, without sacrificing signal-to-noise ratio. And the technique that enabled us to do this is referred to as multiband or simultaneous multi-slice. And this has now become the standard fMRI or even diffusion imaging acquisition strategy. And essentially it's based on the idea that normally you would be acquiring single slices, one slice at a time, or even if you do 3D acquisition, like volumetric acquisition, you would be doing a phase encoding, one phase encode at a time on the third dimension. That's the normal approach. But in this multiband simultaneous multi-slice, you actually excite multiple slices at the same time, and you acquire that data, which is now an image which represents the sum of those slices, and you untangle those slices using the sensitivity profile of an array coil, elements of which have unique sensitivity profile. So these are some original data from the Human Connectome project when we were doing a lot of piloting. So these are multiband simultaneous multi-slice EPI images actually Tesla. So multiband 1 would be your regular EPI, showing 4 slices from the human brain, and multiband 8 would be 8 slices excited at the same time. And you can go to multiband 12 and multiband 16, etc. And you can actually perceive that, for example, especially in multiband 16, you can see the degradation in the image quality. But you can actually evaluate this quantitatively. That was in a paper we published. You can evaluate residual aliasing. For example, if you do multiband 3, you can look at, this is your main slice, and there are two other slices here that have been excited simultaneously. You can see that there is not really any perceptible leakage into those other slices. You can do it for multiband 4, and it still looks good. Multiband 8, okay, there is now starting to have some leakage, but it's really not very bad, and it's usable. But if you go to something like multiband 12, you can see that this so-called leakage actually increases, and based on this evaluation, you can decide where you want to operate. And in the Human Connectome project, we decided to operate for functional imaging for multiband 8. And so these are the parameters that we used. We could achieve 2 millimeter isotropic, multiband 8, and then whole brain coverage was really remarkable, 0.7 seconds. Well, the TE was 33. And then we acquired data, resting state data, 4 times in 15-minute acquisitions. So, and what does that buy us? For example, these are some resting state networks at this 2 millimeter isotropic 3T data. So these are the primary visual cortex networks showing up like these in these 2 slices and sensory motor network. And this is your regular acquisition. And it took us whole brain 5.8 seconds to cover, to get that data for the whole brain. And when we use multiband 8, you can see that the networks are now detected with higher statistical significance And in the motor network, you start seeing other areas, like these supplementary motor areas, which we know are part of the motor network, and they were not detected before. So high sampling rate, in fact, turns out to be very important for resting state fMRI. And so this is what the multiband simultaneous multi-size technology brought us and brought the Human Connect project. So resting state networks now from the 3-test HCP data, you can analyze in many ways. For example, this was an analysis that was performed at the time with high dimensional ICA. So this is 200 components, and then the components are ranked hierarchically, and now you can get these very fine grained networks, so to speak, in this as opposed to networks that are composed of multiple individual networks themselves. And in the Human Connectome project, I was actually, I went into this with the idea of developing technology to improve things, but I had an open mind about what does this resting state networks really tell us? I mean, are they really real? That was being questioned quite a lot, even at that time. But in the Human Connectome project, we have, of course, resting state data, and we also have task data. For example, this is resting state component number 18. It is just the ICA analysis component showing you on the cortex and in the cerebellum what this component 18 looks like. And it looks like, in fact, a motor component. And but we have task data, so we can compare it. What does the task data look like? And we can actually left-hand movement. This is from the Human Connectome project data. On the same individuals, you can see that they actually agree extremely well. In the cerebellum, look at these. It's really a beautiful agreement. And because, of course, there is laterality in motor function, we can look at another component that looks like resting state, the right hand, for example. This is resting state ICA component number 13. It looks like the other hand, and in fact, task fMRI right hand movement, again, there is excellent agreement. So this kind of analysis at the beginning really gave us confidence that the Human Connectome data was really looking very good, and that we had made a major improvement in the quality of the data. There has been many papers coming out of Human Connectome data, and including from our consortium. I don't have time to go into it, but this is just one example that came in Trends in Cognitive Sciences, looking at the fact that we had connectome brain data as well as from different twins and controls. So it's monozygotic twins, dizygotic twins, non-twin siblings, and unrelated pairs. And you can look at the heritability of functional connectivity, and you can see that it's actually large. There's a fairly large heritability component that came out of the Human Connectome project. Now, that was functional imaging. There's, of course, a diffusion-weighted imaging component in the HCP, and that's for, as you know, structural connectivity. And there, the Human Connectome project also made a big leap. Not only, these pulse sequences I told you about is very important for diffusion imaging as well, but there was a hardware component. Diffusion imaging looks at signals that you excite, and then you do a gradient pulse to encode diffusion. You have a refocusing pulse and another gradient pulse. And during this time, before you acquire the data, then there is this diffusion encoding time during which the signal is decreasing. And so it decreases exponentially with the TE. TE is to the center of the K-space here. And one of the things that we did to actually improve that situation is to shorten the TE. And you can do this if you have higher gradient strength gradient. So the Human Connectome 3 Tesla actually had a gradient set of 100 millitesla per meter. These days you can buy these instruments, and many places have them with 100 or even somewhat higher, and then now there are instruments coming up even with higher gradient strength. But this was a big jump at the time, where the gradient strength ran around 40 millitesla per meter. So what does that value? So you can bump up the maximal values of these gradients, and then you can then shorten this. It's the area that is really important underneath those gradients, and so the TE becomes shorter, and in fact you gain SNR by doing this. So this is a very critical part of diffusion imaging. So here are some data that we acquired at the very beginning to see how we were doing. So this is 100 millitesla connectome 3T with 1.25 millimeter isotropic resolution, and this is what was at the time available as a standard instrument, which is like 40 millitesla per meter gradients at 3T, and you can do a 2 millimeter isotropic resolution. You can see that at this even higher resolution, and you have to realize that signal to noise is proportional to the cube of these numbers. So it's the voxel volume has decreased much more than what these numbers 125 and 2 millimeter suggest. But even at this much smaller voxel volume, it's quarter of the voxel volume. So we lost a factor of 4 in SNR due to voxel volume. But still, with 100 millitesla per meter, we are doing better than this gradient at 2 millimeter isotropic resolution. So these are the B values that was used in the Human Connectome project. And just to show you that this did in fact have an impact, and these are some tractography for cortical, thalamic, valgus, spinal, and striatal projections. You put seeds in the up in the cortex, and they should have an organization indicated by these red arrows here. And but you can see that yeah, you can see those things, you expect them, but there are also a lot of false positives in this data at 2 millimeter resolution. But this is the Human Connectome data at 3 millimeter resolution. They come out beautifully, and you can see them very nicely. This is another example of a very difficult track, of connectivity to the pulvinar, and these two different tracks actually come out and twist. And normally they were very difficult to separate, but in Human Connectome data they came out. And I'll show you one more example, which is the arcuate fasciculus. So we put a seed over here, and then we're looking at all those tracks that go through this area, which is where we know that arcuate fasciculus is supposed to be going through. And those are the tracks, coming from the diffusion imaging data, and we have the resting state fMRI data with respect to language areas where arcuate fasciculus is supposed to be active, and you can see that they actually do quite nicely. Now, I don't want to give you the picture that everything is just absolutely fantastic. There are still, limitations to this data, particularly the diffusion imaging data, where you have still, false positives and false negatives. But nevertheless, it was really a major improvement, and this is brain segmentation based on the Human Connectome data. It was a paper published in Nature, and then they labeled it the brain redefined. This was not our suggestion to them, but this is what they came up with, where we identified 180 distinct brain regions per hemisphere based on the Human Connectome data. Now, as I had mentioned, HCP has been successful, based on multiple metrics. For example, these pulse, image acquisition reconstruction sequences. They are really they're available from Minnesota. You can download them and use them. And we support more than 500 sites worldwide with these new image acquisition reconstruction protocols, downloadable from the CMRR webpage. So each site probably has multiple investigators, and as you can see, that it has a huge impact. And these pulse sequences now are available as commercial products from Siemens, Philips, and GE. We only supply, of course, Siemens, because this is the kind of instruments we have. But even in the Siemens world, I have to say, I'm happy to say, even today, even though there's a commercial product, a lot of people still use our sequences. And other initiatives like ABCD, which is still running, or initiatives like that still use Minnesota sequences. And Siemens, Philips, and GE introduced commercial versions of our scanner. So in the Siemens world, it is it operates, I believe, at 80 millitesla per meter, but they are introducing much higher gradients in the near future. And I had to give a talk at NIH and in November 8th last year, and I looked at, we compiled the statistics. So there are 2,261 publications that cite HCP methods. And at the grand number, there were 21,000 approximately users of the Connectome database who have signed the open access data use terms, and there are 1,500 users subscribed to the HCP users email list. And over 27 petabytes of data have been shared to over 20,000 unique users, but that's data, this statistics goes back to fall of 2021. Apparently our tracking service stopped working. So we are still giving out data. This is WashU's responsibility for distributing the data and or disseminating data, but apparently the tracking has stopped. So it has had a huge impact, and I see it all the time. People presenting human connectome-based results, and I believe it has. It's a very gratifying thing to see. And following the Human Connectome project, I mean, NIH was also convinced that that was a successful development, and now there has been, they initiated grants in so-called lifespan human connectome, connectomes related to human disease, developing human connectome, so-called ABCD project that I refer to, etc. So the ABCD is still going on. And these are many of those projects are have wrapped up, and I think that we'll be seeing results coming out of them in the near future. Now, I mentioned that the Human Connectome project had a 7 Tesla component, and that's a really, for me at least, a very important component, but it's a small component, and it's not really well known. And it's not used very much, which is a pity. But I want to tell you a little bit about it, because it sort of actually shows you why there's a future in human connectome type data acquisition beyond what the 3 Tesla component has achieved. So first of all, we discussed quite a bit. What, for example, for resting state fMRI, what should be acquired at 7 Tesla? There was quite a lot of piloting in the Human Connectome project, and all the decisions were made based on extensive piloting data. So this is piloting data from the for trying to decide what should we do in 70. So these are actually a number of ICA components that you can reliably extract from the data if you were to use, for example, 2 millimeter resolution, 1.5 millimeter resolution, down to 0.9 millimeter resolution. And this is where we were at 2 millimeter resolution at ET at a particular significance level. And you can see that 7T data at 2 millimeter resolution does much better than the 3T. But if you try to push it to 0.9 millimeter, and there was some drive to push it to even lower resolutions because of the fact that connectivity is dependent on cortical lamina, and we want to be able to, we were thinking it would be really nice to be able to get resolutions that actually can allow us to separate the different layers of the cortex. 0.9 is not quite enough to do that, but nevertheless it's in that direction. But essentially, when you go to lower and lower resolutions, we lost compared to the 3T, and we ended up right over here at 1.6 millimeter isotropic resolution. So this is 3 Tesla versus 7 Tesla. One was NB8, and this is NB multiband 5. And we had to use, of course, at 7 Tesla acceleration along the phase phase encoding direction, but we use 1.6 millimeter isotropic as opposed to 2 millimeter isotropic. We had, of course, had to have more slices now to cover the whole brain. So the TR for the whole brain acquisition increased, but we still kept it low. That was very important. It was 700 milliseconds at the 3 Tesla, and it was 1000 milliseconds per second at 7 Tesla, and we collected the same amount of data. Now, the 7T data turned out to be, even though it's a higher resolution and a slightly lower sampling rate, 1 second versus 0.7 seconds, had actually quite a lot of advantages over the 3T data. So if you look at number of ICA components, for example, 7T data had approximately twice as much as 3T data. And if you look at contrast to noise, defined as variance relative to unstructured noise, and 7T data, even at this higher resolution, was more than twice as good as the 3T data. And this had real consequences. For example, there's an evaluation of resting state fMRI dense connectomes, cross-run consistency. So what you do is, for a given pair of runs, let's say you take 2 3T runs, same subject, correlates its connectome profile, comes from the dense connectome, you correlate it, and you average over all 3T and then we do this for all 3T and all 7T data within subject run pairs over the same subject population. And we can then average over all subjects, and we can look at that data. So you can see that cross-run dense connectome consistency, how reproducible they are. At 3T, this is what you see. At 7T, this is what you see. So 7T data is considerably more reproducible as shown over here. And these are some resting state networks, if you like, but from a seed voxel placed in the primary visual cortex. And in 3T, you can see a lot of the primary visual cortex, but it's much more extensive in the 7T data. But more importantly, if you look at connectivity, this is from a seed. This is now based on resting state connectivity. So if you put a seed and you say, okay, tell me the connectivity of the seed to the rest of the brain, including the cortical surface, from a subcortical nuclei, and in the human connectome data, this connectivity is really somewhat poor, as you can see over here. And then on the same subject, this is 7T data, and as you can see that now it's considerably more robust and can be visualized. I don't want to say, let me just go back to 3T data, that you cannot get the subcortical to cortex connectivity at 3T. You can. You'll have to use acquisitions which are lower resolution, and so the higher signal noise than what we have used. But this is 2 millimeter isotropic at 3T, and this is 1.6 millimeter isotropic at 7T. So in principle, a higher resolution voxel-wise, a smaller voxel, but yet it does much better at 7T than 3T. Now, diffusion MRI, and there was, and still is sometimes, you encounter this bias that diffusion MRI does not do well at high fields, and there are some reasons for that. Of course, we have the advantage of higher intrinsic signal-to-noise ratio, but there are disadvantages. We have a shorter T2, so SNR is lost faster relative to 3T during diffusion encoding. And then at that time, we did not have the maximal gradient that was available at 3T. So 3T was running at 100 millitesla, and 7T was running at 70 millitesla per liter. So what we did, however, we put that signal-to-noise we had into resolution. So at 3T, the diffusion imaging was acquired with 1.25 millimeter isotropic resolution. In 7T, we went to 1 millimeter. Now again, those numbers suggest that that's a very small difference, but remember, in many ways, signal-to-noise-wise or volumetric resolution-wise, you really have to look at the cube of those because of the fact that we are looking at a volume. So this, when you look at cube of that, this 3T is the voxels are twice as big larger than the 70. It's a factor of 2. So we dropped the B 3000, we stuck the two B values, 1000 and 2000, and there you can see that compared to 3T, we have better signal noise. And but we have now a higher resolution, and here's some fractional anisotropy bands, and you can visually see the effect of the higher resolution. They are crisper at 7 Tesla. And again, some somatotopy, somatotopic organization, for face, hand, and foot area, as those fibers traverse the middle of the brain and these slices, you should see a somatotopic organization like this: blue, green, red. And in 3D, maybe you can see it in the in thalamus and internal capsule, but in 7T data, they start becoming more reliably visible. So even at diffusion, we were seeing some advantages, but there is, in diffusion imaging, people always talk about pulsing fiber problem, but there is yet another problem, and that's the so-called gyral bias problem. So if you look at diffusion imaging tracks, for example, these tracks here, going from one gyrus to the other gyrus, they all go straight to the top of the gyrus. However, this is really not correct, because they should be bending and going to the sulcal banks as well. And this is the so-called gyral bias problem. It's a resolution problem. It is not a diffusion encoded encoding problem. So when we look at that, for example, at 3 Tesla, we're looking at now mean connectivity per surface vertex. So here you can see that all the connections at 3 Tesla, most of them are just going to the top of the gyrus. So that's this gyral bias. But sulcal walls are missing those connections, and this is of course not real, right? There's a lot of connections over there. And in 7 Tesla, 1 millimeter resolution, that problem was quite a bit ameliorated. So there's also a resolution problem, not just a p-value problem. And the 7 Tesla data, this is better achieved in terms of results. So what is next? Well, in many ways, the 7T data that I've showed you kind of indicates what should be next if we are thinking of human connectome type acquisitions and that kind of data to garner information from the human level. So we need higher resolutions. I mean, fMRI, I mentioned to you. For fMRI, functional connectivity at the level of cortical lamina or cortical layers. This is something we discussed, wanted to get to at 7 Tesla in the Human Connectome project, but it was a goal too far for 7 Tesla. And for diffusion imaging, reduction in gyral bias, of course, will result from higher resolution. But also just fiber crossing problem, which is always, or most of the time, cast as a diffusion encoded V value problem, but it also actually is impacted by resolution, and in fact more so than the V values. So ideally, of course, for diffusion imaging, you want high resolution as well as high V values for diffusion encoding. But at any rate, all of these things, if you want higher resolutions and we want higher V values for diffusion encoding, what does this require? It requires higher signal-to-noise ratio. So we've been pursuing, actually, over the years, since the Human Connectome project or through the Human Connectome project, how can we get to higher signal-to-noise ratios in MOR imaging? Well, there are multiple ways, and I want to discuss them very briefly with you. So one is to go to higher magnetic fields. So we launched an effort. This actually predates the Human Connectome. The start of the effort, let's say, predates the Human Connectome project. We started a grant application in 2008, which was funded, but it's a major project that takes a long time. It's a new magnet and helium shortages and everything. So at the end, first images we got from this 10.5 Tesla project in 2017. So it's a decade-long project, but then, even doing 7 Tesla also took a decade. So each time you launch these projects, it's about a decade before you start seeing the fruits. Now, signal to noise, we start talking, everybody talks about, okay, high fields give you signal to noise. But we don't really understand fully, at least we didn't, fully how much signal to noise. There are all sorts of claims and quotations, etc. So we've been looking at this quite extensively, looking at what kind of gains do we have at 10.5 Tesla versus 7 Tesla. Well, one thing is that it's experimentally, it turns out very difficult to determine signal to noise measurements. And so we've been doing a lot of calculations and collaborating with Ricardo Latanzi at NYU to do calculations of ultimate intrinsic SNR. So this is the theoretical maximum SNR you can get at any given magnetic field. It doesn't depend on coil geometry or what kind of coils you use, but it's a theoretical calculation. And then what these calculations showed when you're looking at the ratio of 10.5 Tesla and 7 Tesla is that in the center of the brain, this large yellow-orange area, you get approximately quadratic increase in signal noise, and then as you go towards the periphery of the brain, the signal noise gain decreases linearly. And that has huge implications. For example, let's look at fMRI contrast to noise ratio. That's functional contrast ratio for high resolution imaging. So you can write this function contrast to noise ratio as a signal change. Let's think about task fMRI, but the same thing applies to resting state. So the task fMRI induces some signal change over stimulation, and over noise, which is the temporal signal fluctuation in your time series, that determines your contrast to noise ratio. I can write it in this particular format. So that's delta S, task induced change over the signal intensity over noise. But when I do that, then I should say I can do this. That's a general equation, but when you're looking at high resolution, we know that this noise term is the thermal noise. So we understand quite well, or rather starting to understand quite well, what those terms are if this noise is thermal noise. Well, we know that this is for fMRI, it's the Bowl effect. Well, we've known that for quite a long time. A lot of modeling came out of many labs, including ours. And the modeling shows that this Bowl effect increases linear to quadratically depending on the vessels that are giving rise to it. And the other term, this S over N, is just the image SNR. It's SNR of your MR image. And as I showed you, just from theoretical calculations, we expect that to go somewhere linearly to quadratically, linearly towards the edge of the brain and quadratically over a large central region of the brain. Well, if you combine those two for functional imaging, then we will have somewhere between the square to quadratic dependence on the magnetic field for functional imaging contrast. So that's a huge gain that you can expect from high field. But those SNR gains was theoretical. So do we have any experimental results demonstrating that? And the answer is yes. So, for example, we did a collaboration with Neurospin and Maastricht. Neurospin now operates at 11.7 Tesla. We are at 10.5 Tesla. Maastricht has a 9.4 Tesla, and we all have a 7 Tesla machine. So we had a Phantom. This is a standard Siemens quality control Phantom and Siemens quality control coils. I mean, we all have the same coil. And they're all based on very similar technology. I mean, this looks ergonomically different, but electronically it's very similar. It's a 3 Tesla. It's a bird cage coil for all of these cases. So when you look at the data that you get on this Phantom, as you can see, it looks like maybe it gets worse and worse when you go to higher fields, except in the very center. I won't go into detail why that is the case, but we have to, coil sample interactions are very important. And in this case, we expect actually on the periphery there will be destructive interferences as you go to higher fields, and everything will at some point look very bad. And they do, as you can see here. But in the very center, because of the symmetry of the problem, very center, everything adds constructively. So we can look at the signal noise gain in the center of the sample, and that's a valid measurement. And what we showed is that here are the data from Neurospin in blue, CMRR in green, Maastricht in red, and we all had 7T data. They all agreed very well, surprisingly, and pleasantly surprisingly. And then when we look at the data then over the entire magnetic field, indeed in the center, as the theory predicted, it increased this approximately quadratically, and we theoretically calculated it also showed that it should increase quadratically, and we had the experimental data to show it. Now, of course, that kind of a coil is good for capturing a very small region, but not good for whole brain imaging. We had a very large effort to develop arrays, and these are coming out. One paper came out on it, and another one is just in review. These are major engineering efforts for 10.5 Tesla, and but I won't go into that, but just show you some results. So now we can capture the SNR over the whole brain as opposed to just in the center. And this is 7T data. This is in a phantom that mimics dimensions and the electrical properties of the whole head. This is 10.5 Tesla. You can see that there are really SNR gains a lot in the center, and of course also in the periphery. And we have a 128 channel array as well. And it's a very complex array as shown here. This is developed by Russell Gregor, who's actually also modeling with this coil here. And you can see that. And the transmitter is by Matt Wax. And so these are SNR data plotted as a linear plot by averaging in these thin concentric rings in the sample. Because of the fact that we were talking about center to going out peripherally, they should be different. So for example, this is a 64 channel array, 80 channel array, and 128 channel array. And you can see that actually with 80 and 128 channel array, you start capturing the theoretically expected signal noise gains approximately quadratically in the center, and more than linearly in a large portion of the brain, coming down to linearly at the very periphery. Okay, so we can now have SNR gains. You can demonstrate that they exist in the human brain also. This is the 7T data NOVA coil. This is which is 32 channels. This is 7T data from a 64 channel coil that we built. And this is 10.5 Tesla 64 channels, so you can compare this guy to this guy, and 10.5 Tesla to 80 channel. There are a lot of really important messages about SNR. I don't have time to go into it, but it turned out to be a very complex study. But nevertheless, I want to give you the message that it is complex, but there are significant SNR gains, especially in the center of the brain. And if you in fact want to capture the SNR, you want higher SNR in the center of the brain. For example, if you want a diffusion imaging where white matter tracks are going larger from the center or the subcortical gray matter imaging, you really need high fields to get that. But you also need high channel counts at the same time. Now we haven't done human diffusion imaging at 10.5 Tesla, but we have an ongoing macaque work, and we published data with 580 micrometer isotropic resolution DMRI, led by Jan Zimmerman and Sarah Heilbronner and Isa Yakub in CMRR. This is already published data. And this is fMRI with 500 micrometer isotropic resolution. It's actually laminar fMRI, looking at something called time scales in processing, but with laminar resolution. So this is macaque data. It's ongoing, and higher magnetic field, as I mentioned, it's great. It gives you the SNR you need or you want, but it's really not enough. We need really a lot more SNR to get to this ambition of doing, for example, laminar resting state robustly. So we put a lot of effort also in something else. So higher magnetic fields, of course, yeah, that's they give you potential. By the way, you have to do a lot of associated instrumentation. So magnetic field gives you this intrinsic SNR, but then you have to capture it. That's a different problem and a challenging problem. So we need high channel count receive arrays and different kinds of arrays. We may need other sort of materials and different electronics. And then high performance gradients. This is also extremely important, especially for high fields like 10.5 Tesla. And of course, all of this number 1 and 2 really is to capture what high magnetic fields give you. But then we have to work on image acquisition techniques, and most importantly, image reconstruction and denoising. This is an area that has, I think everybody has now realized the importance of it in every aspect of MRI. There's quite a lot of effort going on in this area. So I'll show you what something we published at the end of 2021 in terms of denoising fMRI data. So this is fMRI data with a particular simulation paradigm, but it's acquired in blocks, 5 minutes blocks. So we have 1 run, 3 runs, and 5 runs, and you can see that this is 7 Tesla data. 1 run or 5 minute data is really not enough to see this. This is a retinotopic stimulation. See this retinotopic stimulation, with a boundary, and the boundary is over here, and the blue is one side, and red is the other side of the retinotopic. And 5 runs looks quite good. But with this denoising technique, which we now call Nordic PCA, you can actually, in 5 minutes of data, you get what you would normally get in about 25 minutes of data. And but the important thing is that you have to be able to do this without blurring, and that's what Nordic does, and with minimal or no impact on the signal components. So we can take out the noise components with really minimal impact on the remaining components, which is what we want. And this is an example of data, 5 mm isotropic resolution, fMRI data, with Nordic. Without Nordic, it's not, 5 mm is a little too far to reach, even at 7 Tesla. And of course, the beauty of this data, as you can see, is that it's really, activation is restricted to the gray matter, and it shows you the laminar profile just right there. You can see it, that the central regions in the visual cortex is supposed to be activated more compared to the peripheral regions, and you can see this very nicely in this data. Now, so we can combine that kind of denoising with 10.5 Tesla, and these are some relatively recent EPI images. And EPI is a very difficult technique at high magnetic fields, but we can accelerate much faster with these high channel count coils. And you can see that these are really beautiful EPI images. I mean, they are, of course, the EPI images are intrinsically crappy. They have these signal dropouts and the nasal cavities, etc. But if you ignore that, I mean, those exist even at 7 Tesla, but this is at 10.5 Tesla. They look, or 3 Tesla will show you. I have to tell you that these images are much better than most EPI images I see at 3 Tesla. So 0.6 millimeter isotropic gain, it's noisier, but this is the kind of data that is really usable for functional resting state, for example. And so we are quite excited about it. And unfortunately, I didn't have a chance to do it, but we have actually fMRI runs now with 0.6 millimeter or 0.65 millimeter isotropic. And that kind of resolution will give you this laminar resolution for resting state. These are just some fMRI runs at 10.5 Tesla with another simulation at 0.8 millimeter resolution. And finally, I want to just very briefly tell you, okay, so this is something that we've been working on, but a major effort that we are involved in right now is so-called Center for Mesoscopic Scale. It's a UN1 grant, Brain Initiative grant, and we are now looking at kind of like the next connectome project, if you like. But that involves both animal models, in this case macaques, as well as human. It involves track tracing, it involves PSOCT, polarized LCT, ex vivo DMRI, human connectome project does not have ex vivo, and in vivo DMRI. And it's a very large group of people. I cannot read all of their names, but we have this large group of people from the University of Minnesota. We have Allen Institute, Cold Spring Harbor, University of Texas, Baylor College, and Sarah Heilbronner is one of the major people leading this effort. We have University of Nottingham, more, we have China here somewhere, right over here, and Chen. So it's actually, it involves many people, 3 continents, Europe, United States, and Asia, institutions in China, US, and UK. And quite exciting, it's a new project, it's about a year old. So I don't have a lot to show you, but since it's an MR talk, I'll show you just a little bit our efforts in ex vivo MRI. And then you can, so we have in vivo, ex vivo, and you can ask why do we want to go to ex vivo. Of course, we can get higher spatial resolution, so we can have in vivo data. We have common signals with ex vivo data, but at higher spatial resolution. And then we can actually also do microscopy, optical imaging, in this case PSOCT, and then we can common tissue between this, and ultimately we want to combine all of those things. And there is of course axonal tissue tracing as well at the single axon level. I won't go into that because of time restriction. But we have challenges. You have ex vivo tissue. You don't have motion problems, you have reduced artifacts, but you have low diffusivity, so you require high p-values, and the signals have a much shorter T2 ex vivo, and we're working at 10.5 Tesla, so you have higher intrinsic SNR, as I talked about, but we have shorter T2 and field inhomogeneities, which are in principle larger as well. But I'll show you some ex vivo data. This is ex vivo DMRI at 10.5 Tesla. This is our own reconstruction, so-called offline reconstruction, with denoising applied to it. Then we have registration and modeling and tractography. This is a B-value of 5,430, which is pretty high B-value. These are SSRT images, so you don't have the distortions that you normally get in PI images. It's not usable, unfortunately, in vivo, but ex vivo works beautifully, and you can see these beautiful diffusion-weighted images in the ex vivo macaque. And all of that I showed you has a big impact in terms of tractography. These are acoustic radiation. This is just the scanner reconstruction of this data. This is our offline reconstruction. You see many more tracks, and then offline with Nordic, and of course with the rest. So I'd like to stop here, and thank you very much for listening. And as I mentioned, there are a lot of people involved in the effort that I talked about, and I've showed some pictures and named some names as we went along. So it takes, sometimes they say it takes a village, but really the things that I talked about, it takes a whole city and multiple cities to accomplish. Thank you for your attention.
Thank you so much for this great talk, Professor Ugurbil. Any questions from the audience? So maybe I'll start with the first question. So you mentioned the imaging reconstruction. So it looks really difficult, like the 10 Tesla. Not everybody has that kind of device, and normally people have 3 Tesla and so on. So how does machine learning and AI kind of techniques can help to fill in the gaps? What's your view about this? We have awesome generative models, diffusion models, and so on. Can we utilize very few high resolution data that we spend a lot of money to acquire very sophisticated devices, and then learn, and then we can generate high dimensional, high resolution images from the signal we acquire in lower, less sophisticated devices?
Yeah, that's a interesting question, and a question that we discussed quite a bit. Yes, I mean, it is, of course, it has, your question has multiple facets. So let me first maybe, the biggest question you're asking: can we learn from the high resolution data, for example, at 10.5 Tesla with these advanced reconstructions, etc., to infer something from data at 3 Tesla? I would say you can learn some things, but you cannot learn everything. I mean, I think that ultimately you really have to, for example, you have to actually infer information at the sub-box. If you look at the 3T data, you are trying to infer information at the sub-voxel level, if you are trying to do that. And that sub-voxel level information is available at 10.5 Tesla to a certain degree. And if you learn from it, okay, you can project this onto the 3 Tesla data because you've learned from AI, but still the 3 Tesla data doesn't have that information. So if things are changed, so let's say that we are interested in, for example, development as ABCD is, or pathology, then we have to learn again all this pathology and all this development, etc. So in principle, you really have to collect a lot of data at the 10.5 Tesla to learn all these different things and to actually project onto the 3T data. So yes, I think that there is some use there, but I'm in general not a very big fan of this kind of, or anticipating there's some utility, but still you need, still at some point you have to have the information, so that means you have to put in the effort for this kind of 10.5 Tesla and image reconstruction. But let me also, maybe there was another secondary question or comment in your question, namely, okay, not everybody has a 10.5 Tesla, and image reconstruction looks complex. I mean, there's not much we can do about not everybody having 10.5 Tesla, but if we can show important gains, then I think that high field machines at 10.5 or 11 Tesla, etc., will increase in number. They're already increasing. I mean, there is now an effort in Holland for a 14 Tesla human machine. I hope it will come to existence. It will be successful. So there are efforts there, and we certainly, once our 10.5 Tesla becomes more stable, and it is becoming very stable in terms of technology, we'll open to outside users. We'll be able to permit dissemination that way. And all these image reconstruction methods, we always distribute them. They're publicly available, and human connectome data acquisition, for example, is a very good example. Most of the world runs with them. And then as we actually develop new reconstructions for the high resolution imaging at 10.5 Tesla, will also make them available. But at any rate, so there will be dissemination, and I think we will need to acquire a lot of data at these very high fields and with these high resolutions.
Yeah. Thank you so much for this extensive answer. Any other questions from the audience? If not, we're going to conclude this section. Thank you so much, Professor Ugurbil. Also,